Thinking about quantum gravity. Chapter 1b, the absence of macroscopic superpositions and the quantum measurement problem. Let's recall once again the two postulates of non-relativistic quantum mechanics. Postulate A, the Schrödinger equation, works beautifully well with experiments. We talked about it last time, that it doesn't explain the absence of macroscopic superpositions. Postulate B, when a quantum system interacts with a classical measuring apparatus, the wave function randomly collapses to one of the eigenstates of the measured observable. For example, a superposition of two eigenstates psi1 and psi2 with complex valued amplitudes A and B collapses to either psi1 with a probability mod A square or psi2 with the probability mod B square. Today we focus on postulate B and the various questions that it raises, which together go under the name the quantum measurement problem. Firstly, how is a classical measuring apparatus defined? What is its mathematical definition? The so-called classical systems are after all made up of smaller quantum systems, and hence the question arises, how large must a system be before we call it classical and before we call it in particular a measuring apparatus? For instance, you start putting together atoms. Firstly, a few atoms, that's a quantum system. Add more, let's say a million atoms. Is it a measuring apparatus now? Or a billion atoms? Is it classical enough to be a measuring apparatus? Quantum theory does not answer this question. So this is one aspect of postulate B, which is already an aspect of concern. What exactly do we mean when we call something a measuring apparatus, a classical measuring apparatus? And again, we are back to this question that the measuring apparatus in fact does not obey the superposition principle. It's classical. A pointer, which is the main part of a measuring apparatus, cannot be here and there at the same time. Otherwise, it would not be a measuring apparatus. If the pointer is to the left, we might conclude that the spin of the incoming particle has collapsed to the state, say, plus half. If the pointer is to the right, we might conclude that the spin has collapsed to the state minus half. But if the pointer itself was in a superposition of pointer to the left and pointer to the right, we won't be able to conclude anything about the measurement. Classical mechanics is supposed to be a limiting case of quantum mechanics. Hence, the measuring apparatus is also a quantum system. So the so-called quantum system on which we are making the measurement and the measuring apparatus together, they form another quantum system. Taken together, the incoming quantum system and the measuring apparatus should both obey the following Schrödinger equation, where the wave function capital Psi now describes both the apparatus and the incoming quantum system. The Hamiltonian is a sum of three parts: the Hamiltonian of the quantum system, the Hamiltonian of the measuring apparatus, and the Hamiltonian which describes their interaction. So, have a look. We have a linear, deterministic Schrödinger equation describing the interaction of the quantum system with the classical measuring apparatus, which in fact is another quantum system. So this equation, being linear, should preserve superposition. If the Schrödinger equation applies in totality to both the apparatus plus the quantum system taken together, which is how things should be, because if quantum mechanics is universal, this should be the Schrödinger equation for the apparatus plus the quantum system, then it should obey superposition. The outcomes of a quantum measurement should also be a superposed state of the two positions of the apparatus. There should be no collapse of the wave function. So why does a measurement break superposition? We don't have an answer for that. In the last set of questions, the Schrödinger equation is deterministic. The initial wave function is specified precisely and hence the final outcome should be exactly known. Why then are the outcomes of measurement random? If the Schrödinger equation has to describe the interaction of the measuring apparatus with the quantum system, the outcomes should have been deterministic because the wave function initially is known exactly. We should know the final state. Then how come that the outcomes are random? Sometimes it's psi1, sometimes it's psi2, and we cannot predict which one it is going to be. We can only tell probabilities of the two outcomes. Now, the big question, where have probabilities come from in a deterministic theory? The Schrödinger equation is deterministic. Absolutely no probabilities in that equation. And when it meets the measuring apparatus, when the quantum system meets the measuring apparatus, lo and behold, we have probabilities. This, in fact, is the only known example of a physical theory in which the initial conditions are precisely known and yet the outcomes are probabilistic and random. And in particular, why do these probabilities obey the Born probability rule and not some other rule? We have this rule only from experiments. The Schrödinger equation does not predict the Born rule. After all, the Schrödinger equation does not even predict randomness or probabilities, let alone predicting the Born rule. Taken together, these questions about postulate B together constitute the so-called quantum measurement problem. This problem has been with us ever since Schrödinger wrote down his equation in 1926, and over this entire period, postulate B and the questions it raises has been discussed intensely, and a vast number of solutions have been proposed. The Copenhagen interpretation says this is how quantum mechanics is. Postulates A and B are fine as they are, and they do not contradict experiments, so we can live with them. That's Copenhagen. Today, this interpretation, the Copenhagen interpretation, is regarded as untenable because of the reasons I've already talked about. We don't expect that there should be a divide between a quantum system and a classical system, namely the apparatus. We have to treat the whole lot together as a bigger quantum system, and then we have a problem because the Schrödinger equation does not apply to the two together as a whole. So, what do we then do about this postulate B? Broadly, there are three classes of explanations. The Manyworlds interpretation says there is no randomness in quantum mechanics, so there is no postulate B really. What happens during the so-called measurement is that the incoming state splits into, say, two branches. In one branch of the universe, the outcome is psi1. In another branch of the universe, the outcome is psi2. The measuring apparatus, the quantum system, and the observer and the whole universe together split into two branches. In one branch, the outcome is psi1. In another branch, the outcome is the state psi2. And this is the so-called Manyworlds interpretation, which in fact is the outcome of how the universe would have to be if the Schrödinger equation applies as it stands to microscopic as well as macroscopic systems. So no randomness means Manyworlds. Okay. On the other hand, we could replace postulate B by the following assertion that there is randomness, but it is in the initial conditions. It is not prescribed by the wave function, the randomness. There are additional degrees of freedom, which used to be earlier called hidden variables, but now the theory is called Bohmian mechanics. So there are additional degrees of freedom, which in the initial conditions are randomly distributed, and depending on what value that initial condition takes, there is one or the other deterministic outcome. So Bohmian mechanics is deterministic. It is just that the initial conditions are random. So we get rid of postulate B by putting all the randomness in the initial conditions. And then there are the collapse models, which say that randomness is there, but it is in the dynamics. The Schrödinger equation is only approximate. It is approximate to a more general dynamics which includes randomness, and the randomness and the generalized dynamics become important only for macroscopic systems. For microsystems, they are negligible. Okay, so this is how we deal with randomness when you go away from the Copenhagen interpretation. In Manyworlds, we say there is no randomness. In Bohmian mechanics, we say there is randomness, but it's in the initial conditions. And in collapse models, we say there is randomness, but it is in the dynamics. In Manyworlds as well as in Bohmian mechanics, the outcomes of experiments are the same as in quantum mechanics. So the experimental predictions of Bohmian mechanics and Manyworlds are exactly the same as that of standard quantum theory, that's by construction. However, collapse models differ in their predictions from the Schrödinger equation, from quantum mechanics, and this is what makes them falsifiable. Okay, some concerns about the Manyworlds interpretation. So this is not to say that the interpretation is wrong. In fact, Manyworlds is a logically consistent explanation of the outcome of measurements, logically consistent resolution of the measurement problem. So what I list below are more subjective concerns, which are my views about what I think are problematic issues with Manyworlds. Firstly, where do the probabilities come from in Manyworlds? Where does the Born rule come from? If there is no collapse, if there is no randomness, if the Schrödinger equation holds universally for all systems, big and small, and if all that is happening is the branching of the universe into many possibilities in which there are different outcomes, then why do we have randomness? Why do we have probabilities? Why are all the outcomes not equally likely? There isn't a satisfactory explanation for this so far. Secondly, the other branches of the universe are inaccessible because we say that the universe has decohered. The different branches do not interact with each other, and that is why we see only one particular outcome of measurement, because the other branch cannot be seen by us. And in this regard, the Manyworlds interpretation is not falsifiable. You cannot do any experiment to find out those other worlds. We don't know how to see them. Our universe does not interfere with those branches. That is decoherence. Environmentally induced decoherence makes the other branches inaccessible, and I think that is unsatisfactory. How do you call something a theory or an interpretation if you cannot test it experimentally? It is indistinguishable from Copenhagen as far as we can tell. And thirdly, if an equation does not agree with the universe, the Schrödinger equation does not agree with what we see, then should we change the equation or should we change the universe? Do I modify the Schrödinger equation as in collapse models, or do I modify the universe that I see to add inaccessible, unfalsifiable branches? Okay, let's have a closer look at the quantum to classical transition, which sheds some light on Manyworlds and collapse models. So we have the Schrödinger equation written on the top left. Let us write the wave function psi as exponential of is by h bar, where s is a complex function. And let's expand s in a power series in Planck's constant. That's the so-called WKB approximation. Then in the macroscopic limit, when the action becomes much larger than Planck's constant h bar, and you retain only leading order terms which are independent of Planck's constant, the Schrödinger equation reduces to the Hamilton-Jacobi equation written in the middle of the slide, minus del s by del t equals h, where s is now to be identified with the classical action of the dynamical system we are studying, h being its Hamiltonian. However, in this explanation of the quantum to classical transition, while we recover Newton's laws of motion from the Schrödinger equation, there is something which we do not recover, and that is the branching. The Hamilton-Jacobi equation, for instance, would give us a solution of Newton's laws of motion. Say if the particle is at some position on the left, you can evolve its motion according to Newton's laws. If it is at some position on the right, again you can evolve its motion according to the Hamilton-Jacobi equation or Newton's laws. But although the Schrodinger equation allows the particle to be at two positions, say on the left and on the right at the same time, you can superpose these two positions. You do not observe such superposition of positions for classical objects, and hence you cannot add two solutions of the Hamilton-Jacobi equation to get a superposed solution. Such solutions are not seen. Although this quantum to classical transition limit, as shown in this slide, this transition method would mathematically allow for superposition of two different classical branches. We don't see them. So you have to observe this carefully, that what is usually taught to us as the quantum to classical transition through the WKB approximation is not the whole story. It does not do justice to what we see. This fails to explain the absence of macroscopic superposition. That's a sort of inbuilt or implicit assumption that we make when we assume that classical mechanics is a limiting case of quantum mechanics. Let's look at the quantum to classical transition once again from the point of view of collapse models. What these models do is they modify the Schrodinger equation as shown in the top of the slide by adding what is known as a nonlinear random process acting on the quantum state psi. So it's assumed that this additional random process which we are adding to the dynamics is negligible for microscopic systems, so that we again have the Schrodinger equation and we have superpositions. But this random process becomes important for macroscopic systems and is what is responsible for branch selection, whether the particle is on the left or whether the particle is on the right. This nonlinear random process breaks superposition, giving rise to random outcomes which disobey superposition and which obey the Born probability rule. So the branch selection would tell you that the particle is either on the left or on the right, but it cannot be in a superposition. That's a consequence of this nonlinearity which is acting randomly now in the dynamics. Furthermore, for macroscopic systems, as before, the Schrodinger equation part of the new modified equation leads to the Hamilton-Jacobi equation either for the left branch or for the right branch, but these two branches now do not interfere with each other precisely because of this nonlinear random dynamics which is now added to modify the Schrodinger equation. So what are we doing here? We are replacing postulate B by a modified Schrodinger equation such that for microsystems the modification in the random nonlinear process is negligible. You have postulate A, namely the Schrodinger equation, but for macro systems the nonlinear randomness is important, and hence instead of having postulate B, you just have a new modified dynamics which does the branch selection for us. The random outcomes according to the Born probability rule are realized because of this modified dynamics. So this is the beauty of collapse models. You don't have to write postulate A or postulate B. You just have a new quantum dynamics, a generalized nonlinear stochastic quantum dynamics which merges postulate A and B together into one new postulate. So this is an alternative to the Manyworlds interpretation where you have only the Schrodinger equation, no modification, no randomness added in the dynamics, and you have the universe splitting into many branches. On the other hand, in collapse model, there is only one universe, no branching into many alternatives, but you have modified the dynamics. And now the experimental predictions are different from those of the Schrodinger equation. So ongoing and future experiments will tell us whether many worlds is right, namely you don't modify the Schrodinger equation, or whether collapse models are right, namely you modify the Schrodinger equation but you don't have universe branching off into many branches. So that is all for today. Thank you for listening. I'll see you next time. Bye.